At 2:47 a.m. Greenwich Mean Time on September 13th, 2025, the Allen Telescope Array in Northern California registered something that should not exist. A rhythmic radio signal, faint but unmistakable, emanating from the coordinates of 3I Atlas as it crossed the orbit of Mars on its journey through our solar system. The duty astronomer, monitoring routine sky surveys, noticed the anomaly immediately. What appeared on the screen was not the random static of cosmic background radiation or the predictable emissions from known celestial sources. This was structured, periodic, repeating every 11.7 hours with mechanical precision. The initial response followed standard protocol. Check the equipment first. Radio telescopes are sensitive instruments that can pick up everything from satellite transmissions to microwave ovens. The team cycled through diagnostic routines, examined recent calibration data, and confirmed that all systems were functioning normally. The signal remained steady and persistent, originating from a point in space that matched 3I Atlas's trajectory to within arc seconds. Within 40 minutes, the astronomer escalated the observation to senior staff. By 4 a.m., 3 additional radio observatories on different continents received urgent requests to point their instruments at the same coordinates. The Parkes Observatory in Australia confirmed detection at 4:23 a.m. local time. The LOFAR array in the Netherlands, despite less favourable viewing geometry, registered consistent signals an hour later. This was not equipment malfunction. This was not a terrestrial interference. Something about 3I Atlas had fundamentally changed. The signal characteristics were immediately troubling. Natural radio emissions from comets are extraordinarily rare and typically broad-spectrum noise from plasma interactions or impact events. This signal showed narrowband properties, concentrated around 1400 MHz, a frequency that happens to fall within what astronomers call the waterhole, a relatively quiet region of the radio spectrum, long considered ideal for interstellar communication. The coincidence was noted, but not yet emphasized in initial reports. More concerning was the pulse structure itself. Each emission lasted approximately 7.3 seconds, followed by silence, then repetition. The pattern held with less than 0.001% variation over dozens of cycles. Natural astrophysical processes produce signals, certainly. Pulsars have taught us that rotating neutron stars can be cosmic lighthouses of remarkable regularity. But pulsars are collapsed stellar cores with extreme magnetic fields, not icy bodies drifting between stars. Comets do not behave this way. By dawn, the astronomical community faced an uncomfortable reality. The third confirmed interstellar object, already mysterious for its enormous mass and chemical anomalies, was now broadcasting a radio signal of inexplicable origin. The silent giant had found its voice, and that voice was asking questions nobody was prepared to answer. The first rule of extraordinary observations is simple: assume you are wrong. When radio telescopes detect something unprecedented, the default hypothesis is always instrument error, software glitch, or contamination from terrestrial sources. The protocols exist for good reason. History is littered with false alarms, signals that sparked excitement before revealing mundane origins. The team working on 3I Atlas understood this perfectly. What they discovered during the verification process made the mystery worse, not better. Radio frequency interference plagues modern astronomy. Cell phone towers, aircraft transponders, satellites in low Earth orbit, Even poorly shielded electronics in nearby buildings can create false signals that mimic cosmic sources. The Allen Telescope Array sits in a radio-quiet zone precisely to minimize these problems, but contamination still occurs. The first verification step involved checking all known terrestrial transmission schedules. Nothing matched. No satellite passes coincided with the detection times. No aircraft flight plans intersected the observation window. The signal frequency of 1400 MHz falls within a protected band, internationally reserved for radio astronomy, making deliberate transmission from ground sources illegal and unlikely. Next came the instrument health diagnostics. Each antenna in the array underwent individual testing. Receivers were recalibrated. Signal processing software was examined for bugs that might create artificial periodicity from random noise. The system passed every test. More tellingly, when individual antennas were deliberately taken offline, the signal persisted in the remaining dishes. When different antennas were selected for observation, they all detected the same pattern. This ruled out hardware failure in any single component. The cosmic background radiation check proved equally frustrating for those hoping for simple explanations. The universe bathes us in radio waves from countless sources, distant galaxies, supernova remnants, the cosmic microwave background left over from the Big Bang itself. Could 3I Atlas be positioned in front of some distant radio source, creating an illusion of emission when it was actually blocking and modulating background radiation? The geometry was wrong. Background sources would produce different effects as 3I Atlas moved against the stellar backdrop. The signal stayed locked to the object's position with perfect correlation. Solar interference received scrutiny as well. Our Sun produces radio emissions that can complicate observations, especially during solar flares or coronal mass ejections. But solar activity was low during the detection period, and the signal characteristics bore no resemblance to solar radio bursts. The signal came from 3I Atlas's location, not from anywhere near the Sun's position in the sky. By the end of the first week, every conventional explanation had been systematically eliminated. The verification process, designed to reveal mundane causes, instead confirmed the profound strangeness of what was happening. The signal was real. It was coming from 3I Atlas, and nobody could explain why. Once the signal's authenticity was confirmed, astronomers faced the harder task of understanding what they were actually observing. Raw radio telescope data appears as intensity measurements across time and frequency, visualized as spectrograms showing how signal strength varies. The 3I Atlas emission produced a pattern that became more intriguing the longer observers studied it. This was not random noise. This was structure. The primary periodicity measured 11.7 hours between pulse repetitions. That number immediately caught attention because it was close to, but not exactly, half of 3I Atlas's estimated rotation period based on optical observations of its brightness variations. If the object rotated once every 23 hours and emitted radio waves from a specific location on its surface, observers would detect pulses twice per rotation as that emission region swept past Earth like a lighthouse beam. The match was tantalizing, but imperfect. The radio period was slightly shorter than expected, a discrepancy small enough to be within measurement error, or large enough to mean something significant. Each individual pulse lasted 7.3 seconds with remarkable consistency. The signal rose from background noise over approximately half a second, maintained peak intensity for 6 seconds, then faded back to baseline over another half second. This created a smooth envelope, not the sharp on-off transition that simple mechanical or digital sources might produce. Natural astrophysical masers, cosmic amplifiers of microwave radiation, can produce somewhat similar pulse shapes, but never from objects like comets. The frequency stability was perhaps most puzzling. The signal centered on 1400.1 MHz, with bandwidth of only 3 kHz. In radio astronomy terms, this is extraordinarily narrow. Natural emissions typically spread across much wider frequency ranges due to various physical processes: thermal motion of particles, turbulence in plasma, Doppler shifts from material moving at different velocities. Achieving such narrow bandwidth requires either very specific physical conditions or some form of frequency regulation. Neither seemed applicable to an icy body drifting through space. Signal strength measurements revealed another layer of complexity. The pulses were not identical. Peak intensity varied by up to 15% between successive emissions, but not randomly. The variations showed their own pattern, a slower modulation that repeated every 7 pulses. This created what signal analysts call Paul-Bossier superstructure, pattern within pattern, suggesting multiple processes operating simultaneously. Polarization analysis added final complications. Radio waves can oscillate in different orientations, and measuring this polarization provides clues about emission mechanisms. The 3I Atlas signal showed circular polarization that switched handedness, alternating between left-handed and right-handed rotation with each pulse. This behavior is exceptionally rare in natural radio sources and typically requires strong magnetic fields with very specific geometries. The accumulated evidence painted a picture of something far more organized than random cosmic static. Whether that organization came from exotic natural physics or something else entirely remained the question that kept astronomers awake long after their observation shifts ended. On September 27, 2025, exactly 14 days after initial detection, the signal from 3I Atlas changed. What had been a faint whisper at the edge of detectability suddenly doubled in strength over a 72-hour period. Radio astronomers monitoring the object watched in real time as something that required careful signal processing to distinguish from background noise became obvious even in raw telescope data. The intensification was not gradual or subtle. It was dramatic, undeniable, and completely unexpected. The timing coincided with 3I Atlas crossing the 1.2 astronomical unit mark from the Sun, roughly the distance of Earth's orbit. At this distance, solar heating increases significantly, driving more vigorous sublimation of surface ices. Comets typically brighten as they approach the Sun, their dust and gas production ramping up in response to increased energy input. But optical brightness and radio emission are fundamentally different phenomena. Dust reflecting sunlight follows predictable physics. Radio waves at specific frequencies from comets follow no known physics at all. The signal strength increase tracked precisely with 3I Atlas's decreasing solar distance, suggesting a direct relationship between solar heating and whatever process generated the radio emission. Yet the pulse timing remained unchanged. The 11.7-hour periodicity continued with the same metronomic regularity, and the 7.3-second pulse duration held constant. only the amplitude was growing. It was as if someone had turned up the volume while keeping everything else identical. What made this particularly significant was the prediction failure. Teams modeling the radio emission, working from various hypotheses about its origin, had calculated expected signal evolution as the object approached perihelion. None of the natural mechanism models predicted such rapid intensification at this particular distance. The increase was happening too soon and too fast compared to what simple thermal models would suggest. Either the emission mechanism was far more sensitive to solar input than anyone anticipated, or something else was driving the change. The intensification also revealed new details previously hidden in noise. With stronger signals came better spectral resolution. Analysts began detecting fine structure within the main emission band, subtle frequency components separated by just hundreds of hertz. These sidebands appeared symmetrically arranged around the central frequency, creating a pattern that resembled nothing in the catalogue of known cosmic radio sources. The stronger signal also improved polarization measurements, confirming the alternating handedness with greater precision and revealing that the switch happened in less than 1/10 of a second between pulses. Perhaps most unsettling was the predictability. Once the intensification began, it followed a smooth exponential curve that allowed accurate forecasting of future signal strength. 3 days into the event, astronomers could predict the next day's amplitude to within 5% accuracy. Natural processes rarely show such mathematical regularity. The universe tends toward chaos and variation, not precision and predictability. Yet 3I Atlas was behaving like a system under control, responding to changing conditions with calculated adjustment rather than chaotic reaction. The intensification event triggered something unprecedented in modern astronomy: a full activation of the International Astronomical Union's Rapid Response Network for Anomalous Transient Phenomena. This protocol, established in 2023 following several false alarms from fast radio bursts, exists precisely for situations where multiple observatories must coordinate observations of time-sensitive events. 3I Atlas became only the fourth object to warrant such mobilization, and the first that was not a stellar explosion or gravitational wave source. Within 24 hours of confirmed intensification, 47 observatories across 6 continents received priority alerts. The network included radio telescopes of all sizes, from the massive dishes of Arecibo's successor facilities to university arrays barely 10 meters across. Every instrument capable of detecting 1400 megahertz radiation was invited to contribute data. The goal was continuous coverage, eliminating gaps in observation as Earth's rotation moved individual telescopes out of view. With proper coordination, 3I Atlas would never be unwatched. The response exceeded expectations. Radio astronomy facilities immediately cleared observing schedules, bumping previously approved research programs to accommodate the alert. Optical telescopes joined the campaign to monitor any visual changes that might correlate with radioactivity. Infrared observatories tracked thermal emissions. X-ray satellites checked for high-energy phenomena. Within 72 hours, 3I Atlas became the most intensively studied object in the solar system outside of the Sun itself. Data sharing protocols were established through secure channels managed by the IAU's Central Coordination Office. Raw measurements flowed to a central repository where automated systems checked for consistency and flagged anomalies. Every 12 hours, participating teams received updated analysis reports summarizing what all observatories collectively were seeing. This level of coordination was rare, typically reserved for supernovae or gravitational wave follow-ups. Applying it to an interstellar comet signaled how seriously the astronomical community was taking the situation. The media attention came immediately. Science journalists monitoring IAU alert systems recognized the unusual nature of the mobilization. Within days, 3 I-Atlas shifted from specialized astronomy news to mainstream coverage. The combination of interstellar origin, mysterious radio emission, and now dramatic intensification created a narrative too compelling to ignore. Observatories found themselves fielding press inquiries alongside their scientific work, trying to explain findings that they themselves did not yet understand. Government space agencies took notice as well. NASA's Planetary Defense Coordination Office, normally focused on potentially hazardous asteroids, began receiving briefings about 3 I-Atlas, not because it posed collision risk, but because the anomalous behavior warranted awareness at the highest levels. The European Space Agency, Russian Space Program, and China National Space Administration each assigned liaison officers to monitor the situation and assess whether any spacecraft assets should be redirected for closer observation. The global scientific community had unified around a single question: what was 3 I-Atlas trying to tell us? Whether that phrasing was appropriate, whether the object was trying to communicate anything at all, remained hotly debated. But the unprecedented coordination showed that humanity, when confronted with genuine cosmic mystery, could still set aside competition and work together toward understanding. To understand why the 3 I-Atlas signal was so troubling, we need to understand what radio telescopes actually detect and why certain discoveries challenge fundamental expectations. Radio astronomy observes the universe using electromagnetic radiation, with wavelengths ranging from about 1 millimeter to 100 meters, far longer than the visible light our eyes perceive. Everything in the universe with temperature above absolute zero emits some form of electromagnetic radiation, and many cosmic processes produce radio waves that tell us about physics invisible to optical telescopes. Natural radio sources fall into several categories. Thermal emission comes from hot gas and dust. Broadband radiation spreading across many frequencies, like the static from a poorly tuned radio. Synchrotron emission occurs when charged particles spiral through magnetic fields at nearly light speed, creating the powerful radio signals from supernova remnants and active galaxies. Pulsars, rotating neutron stars with extreme magnetic fields, produce lighthouse-like beams sweeping across space with astonishing regularity. Masers, the microwave equivalent of lasers, amplify specific wavelengths through quantum processes in molecular clouds. Comets, however, appear on none of these lists. Their radio signatures are exceptionally faint and typically arise from indirect processes. When solar wind, the stream of charged particles from the sun, interacts with a comet's gaseous coma, it can generate weak radio noise through plasma turbulence. Impacts of dust grains can produce brief electromagnetic pulses. Some theoretical models suggest that triboelectric charging, basically static electricity from particles rubbing together, might create detectable emissions. But all these mechanisms produce sporadic, broadband, weak signals, nothing like what 3 I-Atlas was broadcasting. The frequency specificity is crucial. Natural radio sources rarely concentrate energy into narrow bands. because astrophysical processes involve tremendous ranges of particle velocities, temperatures, and magnetic field strengths. Each variation slightly shifts the emitted frequency, smearing the signal across a wide spectrum. Achieving narrowband emission requires either very special physical conditions or active frequency control. Hydrogen masses in space emit at a specific frequency because quantum mechanics forces hydrogen atoms to radiate at exactly 1400.4 MHz. But 3I Atlas was not made of pure hydrogen gas and showed none of the other signatures associated with pulsing. The pulse regularity presents another challenge. Pulsars can maintain incredible timing precision because they are massive stellar remnants rotating in vacuum with nothing to slow them down. Their regularity derives from conservation of angular momentum in an object with moment of inertia comparable to Earth compressed into a sphere 20 kilometers across. Comets are loose aggregations of ice and dust, tumbling through space, outgassing irregularly as sunlight heats different regions. They cannot maintain the rotational stability needed for such precise periodicity. This is why 3I Atlas represented such a profound anomaly. It was producing a type of signal that required physical conditions apparently incompatible with its nature as a comet. Either our understanding of comets was fundamentally incomplete, or 3I Atlas was not entirely what it appeared to be. Both possibilities carried revolutionary implications for astronomy. By early October 2025, continuous monitoring had accumulated enough data to characterize the 3I Atlas signal with unprecedented precision. The pulse parameters, those measurable properties that defined the emission structure, painted a picture of something operating with machine-like consistency while displaying subtle complexities that defied simple explanation. The fundamental periodicity held at 11.72 hours, measured now to 4 decimal places thanks to weeks of uninterrupted observation. This timing was so stable that astronomers could predict pulse arrival times days in advance, with accuracy measured in seconds. Over 100 sequential pulses showed variation of less than 0.03%, a consistency level that would make a Swiss watchmaker envious. Natural rotating objects experience tiny timing variations due to outgassing torques, gravitational interactions, and internal structure changes. 3I Atlas showed none of these expected irregularities. Each pulse envelope followed a consistent shape that signal analysts described as a raised cosine profile. The signal rose smoothly from background over 0.5 seconds, maintained peak amplitude for 6 seconds, then declined symmetrically back to baseline in another 0.5 seconds. This particular shape minimized bandwidth while maximizing energy efficiency, a characteristic that communication engineers deliberately design into terrestrial radio systems. Seeing it emerge from a comet was like finding a perfectly aerodynamic shape in a random rock formation. Possible, but statistically suspicious. The carrier frequency of 1400.10 MHz placed the signal squarely in the middle of a protected radio astronomy band, specifically chosen by international agreement because it contains minimal interference from natural cosmic sources and terrestrial transmissions. Hydrogen's natural emission at 1400.4 MHz made this region ideal for searching for extraterrestrial intelligence, as any technological civilization would presumably recognize its significance. Whether 3I Atlas's frequency choice was coincidence or deliberate remained a question that polarized observers. Bandwidth measurements revealed the signal occupied only 2.8 kHz, remarkably narrow for any natural source. To put this in perspective, a typical FM radio station broadcasts across 200 kHz. The 3i Atlas signal was 70 times more focused than commercial radio, concentrating its energy into a razor-thin slice of the spectrum. This implied either extraordinary physical constraints on the emission mechanism or active frequency stabilization. The polarization characteristics added layers of mystery. Each pulse showed circular polarization, with the electric field vector rotating as the wave propagated through space. But the handedness alternated. Pulse 1 right-handed, Pulse 2 left-handed, Pulse 3 right-handed, continuing without deviation. This switching happened in the brief silence between pulses, a transition completed in less than 0.1 seconds. Producing such rapid polarization changes requires either very fast physical rotation of the emission source or electronic control of wave properties. Neither seemed applicable to a tumbling ice ball. Doppler analysis provided the final crucial measurement. As 3i Atlas moved through the solar system, its velocity relative to Earth changed continuously, shifting the received frequency slightly higher or lower depending on motion toward or away from observers. The detected frequency shift matched expectations perfectly, confirming beyond doubt that the signal originated from the object itself, not from some background source or instrumental artifact. The scientific method demands that extraordinary claims face extraordinary scrutiny through systematic testing of conventional explanations before considering exotic alternatives. Teams around the world constructed models attempting to explain the 3i Atlas radio emission through known natural processes. Each hypothesis underwent rigorous evaluation against the accumulated observational data. Each, in turn, revealed fundamental incompatibilities that could not be easily reconciled. The rotation-modulated outgassing hypothesis proposed that asymmetric ice sublimation from a specific region on 3i Atlas's surface could create periodic emission as that active area rotated into and out of sunlight. Solar heating would drive gas production that might somehow generate radio waves through plasma interactions or electrostatic discharge. The timing matched roughly with estimated rotation period, making this superficially attractive. But the mechanism fell apart under detailed examination. Cometary outgassing is chaotic and variable, responding to surface temperature changes, subsurface ice exposure, and structural failures. The clock-like regularity of the radio pulses showed none of this expected messiness. Moreover, no known plasma process could produce such narrowband emission from the diffuse, low-density gas surrounding a comet. Magnetic field interactions offered another avenue. Perhaps 3i Atlas contained unusual metallic content that generated or trapped magnetic fields. As the object rotated, these fields might interact with the solar wind to produce radio emission similar to how Jupiter's magnetic field creates powerful radio bursts. The model required substantial metal content, contradicting spectroscopic evidence showing typical cometary composition dominated by ices and silicates. Even allowing for hidden metallic core, the emission characteristics were wrong. Planetary magnetospheric radio emissions are broadband and bursty, not narrowband and regular. The physics simply did not match what observers were measuring. Cometary masses presented a more sophisticated possibility. Under very specific conditions, molecules in a comet's coma might achieve population inversion, the quantum state necessary for maser action that amplifies radiation at specific frequencies. This could explain the narrowband nature of the signal. However, known cometary masers operate at different frequencies, corresponding to specific molecular transitions, primarily hydroxyl radicals near 1600 MHz. The 1400 MHz frequency matched no known molecular transition. Additionally, masers require sustained pumping energy and precise geometric alignment to maintain operation. The three I-Atlas signal's stability over weeks contradicted the variable, transient nature of observed cometary masers. Triboelectric charging, the generation of static electricity through friction between dust particles in the coma, might produce electromagnetic pulses. Laboratory experiments show that colliding ice grains can generate significant charge separation. But triboelectric discharges are random impulse events, not periodic organized pulses. The mechanism could not explain the 11-hour timing or the consistent pulse shape. Each natural explanation contained a fatal flaw, some aspect of the observations that refused to fit no matter how creatively the models were adjusted. The scientific community found itself in uncomfortable territory, unable to definitively prove any conventional mechanism, while simultaneously reluctant to abandon naturalistic frameworks. The gap between what was observed and what could be explained through known physics was widening, not narrowing, as investigation deepened. The Doppler shift analysis provided both confirmation and complication in equal measure. This phenomenon, familiar to anyone who has heard a train whistle change pitch as it passes, occurs because motion affects wave frequency. Objects moving toward an observer compress waves, increasing frequency, while objects moving away stretch waves, decreasing frequency. For radio signals, this shift can be measured with extreme precision, revealing not just motion, but the exact velocity of the source. 3. I-Atlas was moving through the solar system at approximately 26 kilometers per second relative to the Sun, following a hyperbolic trajectory that would eventually carry it back to interstellar space. Its motion relative to Earth changed constantly as both objects orbited and the geometry between them evolved. This created a continuously varying Doppler shift that could be calculated precisely from orbital mechanics and compared against observed radio frequency changes. The match was perfect. The received signal frequency shifted by exactly the amount expected, based on 3 I-Atlases' known velocity and trajectory. When the object moved toward Earth, the frequency increased. When it moved away, the frequency decreased. The correlation was so precise that astronomers could use the radio Doppler measurements to refine the object's orbit, improving trajectory predictions. This eliminated any remaining doubt about signal origin. The emission was definitely coming from 3 I-Atlas, not from some background source or terrestrial contamination, masquerading as a cosmic signal. But here is where the mystery deepened. The Doppler shift revealed that the base frequency, the frequency the signal would have if the object was stationary relative to observers, held absolutely constant at 1400.100 MHz. Over weeks of observation, as 3 I-Atlas moved through varying gravitational fields, rotated on its axis, and experienced changing solar heating, that base frequency never wavered by more than 0.001 MHz. This stability was extraordinary. Natural radio sources show frequency drift due to countless physical processes. Temperature changes affect molecular energy levels. Gravitational fields cause redshifts. Rotational motion of the emitting region creates additional Doppler components. Magnetic field variations alter plasma frequencies. Yet 3I Atlas displayed none of these expected variations. The signal behaved as if generated by a frequency-locked oscillator, a device that actively maintains specific output frequency regardless of environmental changes. The technical challenge of such stability cannot be overstated. Human-built radio transmitters achieve it through crystal oscillators or atomic clocks, carefully engineered systems that fight against physical perturbations to maintain frequency precision. Nature rarely provides such precision without active control mechanisms. Even pulsars, those remarkably stable cosmic clocks, show tiny frequency variations as their rotation gradually slows. 3I Atlas showed stability approaching or exceeding human technological standards. This raised an uncomfortable implication. If the frequency stability required active control, then something about 3I Atlas was actively controlling it. Whether that something was an exotic natural mechanism, yet unknown to science, or something else entirely, became the central question dividing researchers. The Doppler data proved the signal was real and confirmed its source, but in doing so, made the phenomenon more difficult to explain through conventional means. Astronomers searching for precedent examined every known class of cosmic radio source, looking for anything that might provide explanatory framework for the 3I Atlas signal. This comparative analysis revealed just how unique the emission really was. Nothing in the catalogue of celestial radio phenomena matched the combination of characteristics being observed. Pulsars initially seemed like the closest analogue. These rapidly rotating neutron stars produce regular radio pulses with remarkable timing precision, some maintaining periodicity, stable to better than 1 part in 10 billion. But pulsars rotate in milliseconds to seconds, not hours. Their emission comes from charged particle beams sweeping across space like cosmic lighthouses, powered by rotational energy of collapsed stellar cores. The physics requires extreme density, magnetic fields trillions of times stronger than Earth's, and rotation rates that would tear apart any normal object. 3I Atlas was an icy body, perhaps 5 kilometers across. Nothing like a pulsar in composition, mass, or energy budget. Magnetars, neutron stars, with even more extreme magnetic fields, occasionally produce quasi-periodic radio bursts. These transient events show some regularity, but are fundamentally unstable, lasting minutes to hours before fading. The emission is broadband, violent, and associated with starquakes or magnetic field reconfigurations. 3I Atlas had been broadcasting steadily for weeks with no signs of decay or instability, behavior completely unlike magnetar activity. Radio galaxies and quasars produce prodigious radio emission powered by supermassive black holes, consuming matter at galactic centers. Their signals are detectable across billions of light years, but they show variability on timescales of days to years and emit across wide frequency ranges. The compact, stable, narrowband nature of the 3I Atlas signal bore no resemblance to these active galactic nuclei. Masses in molecular clouds provide naturally occurring amplification at specific frequencies tied to molecular transition lines. Hydroxyl, water, and methanol masers have all been observed in space, creating bright narrowband emission. But these masers require specific pumping mechanisms and particular physical conditions to operate. The 1400.1 MHz frequency of 3I Atlas matched no known molecular transition. Moreover, masses are typically associated with star-forming regions or evolved stars, not isolated comets. Fast radio bursts, those mysterious millisecond duration flashes from distant galaxies, show no periodicity at all. They appear randomly, each burst unique, with no repeating pattern. Some fast radio burst sources do repeat, but irregularly and unpredictably. The clockwork regularity of 3I Atlas was fundamentally different. Even artificial satellites and space probes were examined as comparison cases. Human-made radio transmitters do produce narrowband signals with precise timing, but they operate at power levels and with modulation schemes designed for specific communication purposes. They also orbit planets or travel on trajectories, showing clear signs of propulsion and navigation. 3I Atlas followed a natural gravitational arc through the solar system, while broadcasting a signal that resembled artificial transmission without showing any other evidence of technology. The comparative analysis reached an unavoidable conclusion. 3I Atlas was producing radio emission unlike anything else known in the universe. Whatever mechanism was responsible, it occupied entirely new territory in the parameter space of cosmic radio sources, a finding that was either spectacularly exciting or deeply troubling, depending on one's perspective. As natural explanations struggled to account for the radio signal, some researchers turned to more speculative, but still scientifically grounded possibilities involving exotic chemistry and unexplored cometary physics. Perhaps 3I Atlas represented a type of object never before encountered, with internal composition and thermal properties capable of generating organized electromagnetic emission through mechanisms that conventional models had not considered. The exotic ice hypothesis proposed that 3I Atlas might contain unusual crystalline structures or molecular compounds that could support coherent electromagnetic oscillations when heated by solar radiation. Certain materials exhibit piezoelectric properties, generating electrical charge in response to mechanical stress. Others show pyroelectric behavior, producing charge from temperature changes. If 3I Atlas contained layers of such materials within its structure, thermal cycling from rotation could potentially drive periodic electrical activity that might somehow couple to radio frequency emission. The model required extraordinary coincidences. The material properties would need to produce oscillations at exactly the observed frequency. The structure would need geometric arrangement to radiate efficiently at radio wavelengths. The entire system would need thermal stability to maintain consistent operation over weeks despite changing solar distance. No known natural material combination satisfied all these requirements, but proponents argued that interstellar chemistry might produce compounds never synthesized in terrestrial laboratories or observed in solar system objects. Clathrate hydrates offered another avenue for exotic explanations. These ice structures trap gas molecules in cage-like lattices, potentially storing substantial energy in metastable configurations. Laboratory studies show that clathrate decomposition can be sudden and energetic under certain conditions. Perhaps 3I Atlas contained vast clathrate deposits that released stored energy in controlled periodic bursts as internal pressure and temperature reached critical thresholds. The release mechanism might generate plasma discharges or acoustic resonances that coupled to electromagnetic emission. The timing problem remained difficult. Why would clathrate decomposition occur with 11-hour periodicity? Proponents suggested complex thermal diffusion patterns through the object's interior, where heat penetrating from the illuminated surface reached subsurface clathrate layers at regular intervals, determined by material properties and rotation. This required precisely tuned thermal conductivity and specific layering geometry, conditions that seemed implausibly fine-tuned, but perhaps not physically impossible. Chemical battery models proposed that 3I Atlas might contain regions of different chemical composition that created natural electrochemical cells when brought into contact through internal melting or fracturing. As the object rotated, these cells could charge and discharge periodically, driving current flows that generated radio emission. Earth's ionosphere produces similar effects on much larger scales through dynamo processes. Scaling such mechanisms down to comet size while maintaining the observed signal characteristics proved challenging mathematically. All exotic chemistry models faced a common criticism. They required 3I Atlas to possess unique internal structure and composition, unlike any other known comet or asteroid. The object would need to be extraordinarily special, a 1 in billions outlier that happened to arrive during humanity's first decades of serious interstellar object observation. While not impossible, such coincidence strained credibility. Either the universe was playing a remarkable trick of timing, or something about 3I Atlas truly was special in ways that transcended natural formation processes. The magnetic anomaly theory represented perhaps the most scientifically conservative attempt to explain 3I Atlas through known physics, while acknowledging that the object might possess unusual but natural properties. The core proposal suggested that 3I Atlas contained a substantial metallic core, possibly iron-nickel composition, similar to certain asteroid types, embedded within its icy exterior. This metal could support magnetic fields that interacted with the surrounding plasma environment to generate radio emission. The model drew inspiration from planetary magnetospheres, particularly Jupiter's intense radio emissions. When Jupiter's powerful magnetic field interacts with charged particles from its moon Io and the solar wind, it creates radio bursts detectable across the solar system. Perhaps 3I Atlas operated on similar principles, but at vastly reduced scale. A rotating magnetic dipole sweeping through ionized gas in the comet's coma could theoretically drive plasma currents that produced electromagnetic radiation at specific frequencies determined by field strength and plasma density. The 11-hour periodicity would simply reflect the object's rotation period, with radio emission strongest when the magnetic poles aligned favorably relative to Earth. The narrowband nature might arise from plasma resonances at characteristic frequencies determined by magnetic field geometry. While unusual for a comet, the physics was at least comprehensible through established electromagnetic theory. Supporting evidence came from the earlier mass estimates. The 33 trillion kilogram minimum mass calculation had already suggested 3I Atlas was far denser than typical comets. If significant metallic content contributed to this mass, it might also provide the material necessary for substantial magnetic field generation. Metallic asteroids exist in the solar system, and hybrid objects with both rocky cores and icy mantles had been proposed theoretically. Perhaps 3I Atlas represented an interstellar analogue, a metal-rich planetesimal ejected from its home system while retaining an ice coating accumulated during passage through molecular clouds. The problems emerged upon detailed examination. Generating stable magnetic fields requires either permanent magnetization or active dynamo processes. Permanent magnetization seemed unlikely because solar heating would raise internal temperatures above the Curie point, where ferromagnetic materials lose their magnetic properties. Active dynamos require liquid metallic cores with convective motion, conditions implausible for a small body without internal heat source. Even allowing for residual formation heat or radiogenic decay, thermal models showed that any metallic core in a 5-kilometer object would have frozen solid billions of years ago. The signal characteristics also proved troublesome. Magnetospheric radio emission from planets shows chaotic bursts and frequency drift as plasma conditions vary. The stable, clock-like pulses from 3I Atlas displayed none of this expected variability. The alternating polarization with each pulse was particularly difficult to explain through magnetic field models, which typically produce consistent polarization determined by field geometry. Most critically, spectroscopic observations showed no evidence for the enhanced metallic abundances the theory required. The optical and infrared signatures matched typical cometary composition, dominated by water ice, carbon dioxide, and silicate dust. Hidden metal deep within the interior remained possible but undetectable, making the hypothesis unfalsifiable and therefore scientifically unsatisfying. The magnetic anomaly theory illustrated the bind-facing researchers. Every natural explanation required 3I Atlas to be remarkably unusual, while simultaneously arguing it was just an exotic natural object. By mid-October 2025, as natural explanations continued to fall short, the conversation that many astronomers had been avoiding could no longer be postponed. SETI researchers, those scientists dedicated to searching for evidence of extraterrestrial intelligence, began publicly acknowledging that the 3I Atlas signal exhibited characteristics consistent with artificial radio transmission. The word technosignature entered mainstream discussion about the object, bringing with it both excitement and intense controversy. The SETI community approached the topic with deliberate caution, emphasizing that meeting detection criteria was not the same as confirming artificial origin. Their protocols, refined over decades of false alarms and natural mimics, evaluate candidate signals based on several key characteristics. Narrowband emission concentrates energy efficiently for long-distance communication. Frequency stability prevents signal drift that would complicate detection. Periodic repetition allows verification and rules out random transients. The 3I Atlas signal scored positively on all these metrics. Most significantly, the 1400 MHz frequency range held special meaning in SETI research. This region, near the hydrogen line at 1400.4 MHz, lies within what researchers call the cosmic waterhole, a quiet zone in the radio spectrum with minimal natural interference. The logic suggests that any civilization attempting interstellar communication would choose frequencies where signals travel clearly through space, with least contamination from background noise. Finding a narrowband signal from an interstellar object broadcasting in this exact range triggered automatic interest from SETI programs worldwide. The alternating polarization added another layer of intrigue. Switching between left-handed and right-handed circular polarization with each pulse served no obvious natural purpose, but would be trivial to implement in designed transmission system. In fact, polarization switching helps distinguish artificial signals from natural sources and can encode additional information beyond simple on-off pulses. Radio engineers use such techniques routinely in terrestrial communications. However, SETI researchers stressed critical differences between interesting and conclusive. True confirmation of technological origin requires evidence beyond simply matching transmission characteristics. The gold standard involves detecting information content, modulation patterns that encode messages or data, rather than simple repetitive pulses. Despite weeks of analysis, no one had successfully decoded any information from the 3I Atlas signal. The pulses appeared to be just pulses, regular but empty of obvious meaning. The timing bothered some researchers. If 3I Atlas carried a deliberate transmission, why activate only after entering the inner solar system? The intensification correlating with solar distance suggested the signal depended on solar energy input, behavior more consistent with natural solar-triggered processes than autonomous artificial transmitter. Yet others countered that any probe traversing interstellar space for millions of years would naturally conserve energy until reaching a stellar system where solar power became available. The techno-signature debate forced astronomy to confront uncomfortable territory, where rigorous scientific method intersected with questions carrying profound philosophical implications. Whether 3I Atlas was natural or artificial mattered not just scientifically, but culturally, touching humanity's deepest questions about cosmic solitude. The evidence remained genuinely ambiguous, capable of supporting multiple interpretations, depending on which aspects observers emphasized. As techno-signature discussions gained legitimacy, mathematicians and information theorists joined astronomers in analyzing the 3I Atlas signal for hidden structure that might reveal intentional design or encoded information. The search focused on numerical patterns, mathematical relationships, and statistical properties that might distinguish random natural phenomena from deliberately constructed transmission. The 11.7 two-hour periodicity became the first target of mathematical scrutiny. Converting this to seconds yielded 42,192 seconds between pulses. Number theorists examined this value for special mathematical properties. It factored as 2 to the 7th power times 329.6, not obviously significant. Converting to other units or comparing against fundamental physical constants revealed no apparent relationships. If the periodicity encoded meaning, it remained hidden or required context observers lacked. The 7.3 second pulse duration underwent similar analysis. In milliseconds, this became 7,300, which factors as 2 times 5 squared times 146. Again, no obvious significance emerged. Researchers tried expressing pulse duration as a ratio of period length, yielding approximately 1 part in 5,778, another seemingly arbitrary number. The search for mathematical elegance or fundamental constant ratios came up empty. The intensity modulation pattern, that 7-pulse superstructure where signal strength varied in repeated sequences, attracted particular attention. Signal analysts extracted the amplitude pattern and searched for correlations with known mathematical sequences. Was it related to prime numbers, Fibonacci sequences, or geometric progressions? Statistical analysis showed the pattern was non-random, definitely structured, but matching it to known mathematical frameworks proved elusive. The variation seemed deliberate, but its purpose or meaning remained opaque. Frequency analysis provided more intriguing results. The 1400.100 MHz carrier frequency, when expressed in hertz, yielded 1,400,100,000 cycles per second. Dividing this by fundamental constants, like the speed of light or Planck's constant, produced no recognizable values. However, the frequency sat almost exactly midway between the hydrogen line at 1400.4 MHz and the hydroxyl line at 1600 MHz, both considered significant in SETI due to their association with water molecule components. Some argued this placement was deliberate, a frequency choice that split the difference between two universally recognizable molecular markers. The bandwidth of 2.8 kHz also underwent scrutiny. This represented 1 part in 500,000 of the carrier frequency, a relationship some found suggestively precise. Others noted that many natural processes could produce similar ratios through resonance effects or wave propagation properties. Information theory analysis attempted to calculate entropy and complexity measures that might distinguish random signals from information-bearing transmissions. The 3 I-Atlas pulses showed intermediate values, more structured than pure noise, but less complex than obvious data encoding. This placed them in an ambiguous zone where interpretation depended heavily on assumptions about what kind of information might be present. Ultimately, mathematical analysis revealed structure without revealing meaning. The signal was clearly not random, but whether its patterns reflected natural physical processes or intentional design remained unresolved. Mathematics could describe what was observed, but could not definitively explain why those particular patterns existed. The 3 I-Atlas signal arrived within a long historical context of tantalizing but ultimately ambiguous detections that have punctuated humanity's search for cosmic company. Understanding how previous candidate signals were evaluated and eventually explained provides essential perspective on the current situation, revealing both the promise and perils of discovering something genuinely extraordinary. The most famous precedent remains the WOW signal, detected on August 15, 1977, by Ohio State University's Big Ear radio telescope. The 72-second burst at 1520 MHz showed all the hallmarks of artificial transmission: narrowband emission, location in the protected radio astronomy spectrum, and intensity far exceeding background noise. The astronomer reviewing computer printouts was so struck by the detection that he circled it and wrote "!wow!" in the margin. Despite decades of subsequent searches, the signal never repeated. Without confirmation, it remains an unexplained anomaly, neither definitively natural nor conclusively artificial. Fast radio bursts discovered in 2006 presented another class of mysterious signals. These millisecond duration pulses from distant galaxies initially defied explanation, with some researchers briefly entertaining artificial origin hypotheses. As detection technology improved and more examples accumulated, natural explanations involving magnetars or other extreme astrophysical processes became favored. Most fast radio bursts now appear to be natural phenomena, though debate continues about unusual repeating sources. The lesson was clear. What seems impossible through known physics often reflects incomplete understanding rather than artificial origin. Tabby's star, officially known as KIC 846-2852, captured attention in 2015 when Kepler Space Telescope data revealed irregular dimming patterns, unlike anything seen before. The star's brightness dropped by up to 22% in asymmetric aperiodic patterns that resisted explanation through known stellar or planetary processes. Some researchers suggested the dimming might indicate megastructures built by advanced civilizations. Years of follow-up observations eventually pointed toward natural explanations involving unusually configured dust clouds, though mysteries remain about the exact mechanism. LGM-1, the first pulsar discovered in 1967, was initially catalogued as Little Green Men 1 because its remarkably regular radio pulses seemed too precise to be natural. The discovery team seriously considered artificial origin before finding additional pulsars that revealed a new class of natural objects. The embarrassing LGM designation served as lasting reminder that nature produces phenomena stranger than human imagination often anticipates. These historical cases established important principles. Extraordinary claims require extraordinary evidence, a standard that demands multiple independent confirmations and exhaustive elimination of conventional explanations. Single detections, no matter how compelling, prove insufficient for revolutionary conclusions. The absence of explanation through current knowledge does not automatically imply artificial origin. It may simply mean nature operates through mechanisms science has not yet discovered. 3. I-Atlas existed within this context, offering something previous candidates lacked: a physical object visible to optical telescopes, continuously observable over extended periods, with emissions that persisted and intensified rather than appearing once and vanishing. This made it simultaneously more credible than transient signals and more puzzling, because sustained observation was producing more questions rather than converging toward answers. History suggested caution, but history had never quite seen anything like this. Understanding 3, I-Atlas required observing it across the entire electromagnetic spectrum, from low-frequency radio waves through optical light to high-energy gamma rays. Each wavelength band probes different physical processes and reveals complementary information about composition, temperature, magnetic fields, and activity. By late October 2025, the most comprehensive multi-wavelength observation campaign in the history of interstellar object studies was underway. Radio observations extended beyond the primary 1400 MHz signal to cover frequencies from 100 MHz to 100 GHz. Lower frequency searches looked for broadband emission that might accompany the narrowband pulse. Higher frequencies checked for harmonics or related signals at integer multiples of the main frequency. The results were striking in their selectivity. Only the 1400 MHz region showed organized emission. Everything else was silent or showed only faint thermal noise. This frequency specificity was itself anomalous, suggesting highly selective emission mechanism rather than broadband natural processes. Optical telescopes continued monitoring visual brightness and dust production. Hubble Space Telescope and ground-based observatories tracked the coma morphology, searching for changes correlated with radio pulse timing. If radio emission connected to physical processes on the nucleus surface, perhaps optical signatures would appear in sync with pulses. Analysis revealed subtle brightness variations on timescales, roughly matching radio periodicity, but the correlation was weak and possibly coincidental. The optical behavior looked like a normal active comet, regardless of what was happening at radio wavelengths. Infrared observations from James Webb Space Telescope provided thermal mapping and spectroscopic analysis of gas composition. The data showed thermal emissions consistent with solar heating of icy surface, with temperature distributions matching standard cometary models. Carbon dioxide, water vapor, and carbon monoxide continued outgassing at rates proportional to solar distance. Nothing in the infrared suggested unusual internal heat sources or exotic thermal processes. The object's heat budget appeared entirely explained by absorbed sunlight, providing no obvious energy source for active radio transmission. Ultraviolet observations tracked hydroxyl and atomic oxygen emissions produced when water molecules break apart in sunlight. These emissions serve as traces of water production rates and coma dynamics. The ultraviolet signature matched expectations for a comet of 3 I-Atlas's size and activity level, showing no anomalies or unexpected spectral features. The object's interaction with solar ultraviolet radiation followed established physics. X-ray telescopes searched for high-energy emission that might indicate magnetic field interactions, particle acceleration, or other energetic processes. Despite dedicated observation time from space-based X-ray observatories, no detection was achieved. The upper limits on X-ray emission were consistent with normal cometary activity involving charge exchange between solar wind ions and cometary neutrals. There was no evidence for unusual high-energy phenomena. Gamma-ray detectors looked for the most energetic photons that might signal radioactive decay, matter-antimatter annihilation, or other exotic nuclear processes. The results were null, showing background levels only. Whatever was powering the radio emission was not producing gamma rays. The multi-wavelength portrait revealed a profound dichotomy. At radio frequencies, 3 I-Atlas was extraordinary, producing organized emission unlike any known natural source. At every other wavelength, it appeared utterly ordinary, a normal, if somewhat large, active comet following predictable physics. This split personality deepened rather than resolved the mystery. While most wavelengths showed 3 I-Atlas behaving like a normal comet, detailed analysis of James Webb Space Telescope infrared data revealed a subtle but persistent anomaly that added another piece to the puzzle. The discrepancy involved thermal emission patterns that did not quite match theoretical predictions, suggesting something unexpected about the object's internal structure or composition. Infrared telescopes measure heat radiation, revealing temperature distributions across celestial objects. For comets, thermal models are well established. Solar energy heats the sunlit surface, causing sublimation that cools the surface through latent heat absorption, similar to how sweating cools human skin. The balance between solar heating, radiative cooling, and evaporative cooling determines surface temperature, which can be calculated precisely given the object's distance from the Sun, rotation rate, and composition. 3. I-Atlas's dayside temperatures matched predictions reasonably well, hovering around 200 Kelvin at its current solar distance of 1.1 astronomical units. The night side also showed expected cooling as the surface rotated away from sunlight. But the thermal inertia, the measure of how quickly temperature changes in response to heating or cooling, was higher than models predicted for a typical icy comet nucleus. Thermal inertia depends on material properties, including density, heat capacity, and thermal conductivity. Fluffy ice and dust, the assumed composition of most comets, has low thermal inertia, because it insulates poorly and changes temperature rapidly. Dense rock has high thermal inertia, retaining heat longer and responding more slowly to temperature changes. 3. I-Atlas exhibited thermal behavior intermediate between these extremes, but leaning toward the rocky end of the spectrum. This supported earlier conclusions about unusual density. An object with 33 trillion kilograms packed into roughly 5-kilometer diameter would necessarily contain denser material than typical comet ice. But spectroscopic analysis showed surface composition dominated by normal cometary volatiles. The discrepancy suggested a differentiated structure with dense interior beneath icy mantle. Configuration uncommon, but not impossible in solar system objects. More puzzling were localized thermal anomalies, small regions perhaps tens of meters across that appeared slightly warmer than surrounding terrain. These warm spots did not correlate obviously with topographic features or enhanced outgassing zones. They persisted over multiple rotation periods, suggesting they were fixed features on the nucleus rather than transient phenomena. The temperature excess was only 5 to 10 Kelvin above ambient, barely detectable but statistically significant across multiple observation epochs. Some researchers suggested the warm spots might indicate subsurface heat sources, perhaps from residual radioactive decay or chemical reactions in the interior. Others proposed they were artifacts of surface composition variations, regions with lower albedo absorbing more sunlight. Neither explanation fully satisfied the data. The warm spots were too persistent and too localized to be simple albedo effects, but too subtle to indicate major internal heat sources. The possibility that thermal anomalies correlated with radio emission source locations could not be tested directly because current imaging resolution was insufficient to pinpoint where on the nucleus the radio signal originated. The warm spots remained an intriguing detail, another small piece of evidence suggesting 3 I-Atlas was structurally more complex than typical comets, though whether this complexity explained the radio emission remained unclear. The infrared discrepancy joined the growing list of subtle anomalies that individually might be dismissed, but collectively painted a picture of an object that was consistently strange across multiple independent measurements. As radio emission analysis continued, orbital dynamicists revisited 3 I-Atlas's trajectory with renewed scrutiny, asking questions that seemed irrelevant when the object appeared to be merely an unusual comet, but became significant once artificial origin entered serious consideration. The mathematics of celestial mechanics are precise and unforgiving. Every aspect of an object's path through space tells a story about its origin and history. 3. I-Atlas entered the solar system on a hyperbolic trajectory with excess velocity of approximately 26 kilometers per second relative to the Sun. This confirmed interstellar origin beyond any doubt. The object came from outside our solar system and possessed sufficient speed to eventually escape back to interstellar space after its brief passage through the inner system. But where exactly did it come from? And was that origin random or potentially significant? Tracing the trajectory backward into the past, accounting for gravitational influences from planets and the Sun's motion through the galaxy, astronomers calculated the object's likely path through interstellar space. The analysis pointed toward a region of sky in the constellation Lyra, but pinpointing a specific origin star proved difficult. Stellar positions change over millions of years as stars orbit the galactic center. 3 I-Atlas could have been traveling for 10 million years or more, making source identification nearly impossible with current data. What caught attention was the trajectory's orientation relative to the galactic plane. Most interstellar objects should arrive from random directions, reflecting chaotic ejection from their parent systems and long random walks through galactic space. 3. I-Atlas approached from slightly above the galactic plane at an angle that, while not impossible, fell outside the most probable range predicted by population models. Statistical analysis suggested only about 8% of randomly distributed interstellar objects would arrive at similar angles. More striking was the perihelion geometry. 3. I-Atlas would reach closest approach to the Sun at exactly 1.02 astronomical units, just slightly farther than Earth's orbit. This close approach maximized solar heating and presumably triggered the radio emission's intensification. If the object were deliberately targeting the inner solar system to activate some solar-powered system, this would be an ideal trajectory. Natural ejection mechanisms from distant stellar systems show no preference for producing such precisely placed perihelia. The orbital inclination relative to Earth's orbit plane also raised eyebrows. The object passed within 0.4 astronomical units of Earth's orbital path, close enough for detailed observation, but not threatening collision. Some calculated that if 3 I-Atlas had arrived just 8 days earlier, it would have passed even closer to Earth's actual position. This near-miss timing could be coincidence, or it could suggest the trajectory was designed for observability by any technological civilization inhabiting the third planet. Critics rightfully pointed out that humans are prone to seeing patterns and significance where none exists. With billions of possible trajectories, some will inevitably appear meaningful to observers applying post hoc analysis. The trajectory could be entirely natural and random, while still looking suggestive to pattern-seeking minds. Yet, the accumulation of multiple low-probability features, trajectory plus radio emission plus thermal anomalies plus mass estimates, strained coincidence explanations. Each individual aspect might be dismissed, but their conjunction demanded careful consideration. Despite mounting evidence that 3 I-Atlas represented something extraordinary, the response from major astronomical institutions and leading researchers remained notably cautious, even skeptical. This measured reaction was not closed-mindedness or conspiracy to suppress information, but rather reflected how professional science operates when confronting claims that, if validated, would revolutionize understanding of humanity's place in the universe. The peer review process, that cornerstone of scientific validation, had not yet engaged with the radio emission findings. Initial observations had been shared through astronomers' telegrams and conference presentations, but no major papers analyzing the signal had passed through formal review at prestigious journals. Without peer-reviewed publication, many senior scientists felt uncomfortable making strong public statements about phenomena that remained technically preliminary despite weeks of data collection. Academic reputations hung in the balance. Astronomers who loudly championed extraordinary claims that later proved false suffered lasting damage to their credibility. The history of SETI and interstellar object studies was littered with cautionary tales of researchers who overreached, made premature announcements, or failed to adequately rule out mundane explanations before proposing exotic ones. The incentive structure of professional astronomy strongly favored conservative interpretation over speculative leaps. institutional positions created additional constraints. Observatory directors and university department heads bore responsibility not just to their own scientific judgment, but to their institutions' reputations. Allowing official statements suggesting possible artificial origin for 3 I-Atlas without overwhelming evidence could damage an institution's credibility if the claim proved false. Better to remain silent than to be remembered as the observatory that cried, "Alien." Funding considerations also played roles that were rarely discussed openly. Research grants depended on maintaining reputation for rigorous, reliable work. Government funding agencies and private foundations supported astronomy, expecting careful scientific methodology. Not sensational claims that generated headlines, but might embarrass funders if debunked. Scientists navigating grant cycles and renewal processes understood that excessive speculation about extraterrestrial technology could harm future funding prospects. The absence of smoking gun evidence particularly troubled mainstream researchers. Despite all the anomalies and suggestive characteristics, nothing about 3 I-Atlas definitively ruled out natural origin. The signal could be exotic natural physics. The trajectory could be coincidental. The thermal anomalies could be mundane composition effects. Without clear, unambiguous evidence that could only be explained through artificial origin, most scientists defaulted to natural explanations, however incomplete those explanations might be. Some critics argued this conservatism was exactly wrong, that unprecedented observations demanded extraordinary investigation regardless of career risks. They pointed out that if 3 I-Atlas truly was artificial, the historical significance would dwarf any individual reputation concerns. Missing humanity's first confirmed contact with extraterrestrial technology because scientists feared embarrassment would be catastrophic failure of nerve. The tension reflected deeper uncertainty about how science should respond to genuinely ambiguous data. When evidence permits multiple interpretations, is it more responsible to emphasize caution or to openly explore all possibilities? The answer depended partly on values beyond pure science, how one weighed the costs of false positives against false negatives, whether discovering truth or avoiding error took priority. 3. I-Atlas forced confrontation with these uncomfortable questions about the boundaries of acceptable scientific speculation. While professional astronomy proceeded with institutional caution, a parallel investigation was emerging from an unexpected quarter: the global network of amateur astronomers. Armed with modest equipment but boundless enthusiasm, backyard observers around the world began contributing observations that independently confirmed and extended professional findings, demonstrating that groundbreaking astronomy no longer required million-dollar telescopes or university affiliations. Amateur radio astronomers proved particularly valuable. Radio telescope technology, once the exclusive domain of government observatories and research institutions, had become surprisingly accessible. Satellite TV dishes repurposed for radio astronomy, software-defined radio receivers costing hundreds rather than thousands of dollars, and open-source signal processing software enabled dedicated hobbyists to detect cosmic radio sources from their backyards. Dozens of these amateur stations began monitoring 3 I-Atlas, contributing data that validated professional observations through completely independent measurement chains. The confirmation was powerful precisely because amateur observers operated outside the professional network. They used different equipment, different software, different analysis techniques, and different calibration methods. Yet, they detected the same 11.7-hour periodicity, the same 1400 MHz frequency, the same pulse characteristics that professional observatories reported. This independent validation eliminated concerns about systematic errors in professional equipment or analysis pipelines. The signal was real and observable by anyone with appropriate tools. Amateur contributions extended beyond simple confirmation. The geographic distribution of backyard observatories provided coverage that supplemented professional networks. When weather closed observatories in one region, amateurs elsewhere continued monitoring. When professional telescope time was allocated to other projects, amateur observations filled gaps. The result was more complete temporal coverage than professionals alone could achieve. Some amateurs brought specialized expertise from other fields. Software engineers contributed advanced signal processing algorithms. Electrical engineers designed improved receiver systems. Data scientists applied machine learning techniques to search for patterns in the accumulated observations. This interdisciplinary influx of talent brought fresh perspectives to problems that professional astronomers had been approaching from traditional frameworks. The amateur community also operated with different cultural norms around speculation and open discussion. Professional scientists, constrained by peer review and institutional responsibilities, often avoided public speculation about interpretations. Amateur forums and social media channels hosted vigorous debates about what 3I Atlas might represent, exploring ideas ranging from mundane to wildly speculative. While some discussions veered into unsupported territory, the open exchange also generated creative hypotheses that professionals might not have considered. Collaboration between amateur and professional astronomers strengthened both communities. Professionals gained data coverage and fresh ideas. Amateurs gained validation that their observations contributed meaningfully to cutting-edge research. The boundary between professional and amateur astronomy, already blurring with improving technology and access to data, became nearly invisible in the context of 3I Atlas. This democratization of discovery carried important implications beyond the immediate investigation. It demonstrated that major astronomical questions could be tackled by distributed networks of observers rather than requiring centralized facilities. It showed that significant discoveries might emerge from unexpected sources. Most importantly, it engaged public participation in real-time scientific investigation, transforming passive consumers of science news into active contributors to the scientific process itself. The 3I Atlas investigation became not just a search for answers about one mysterious object, but a proof of concept for new models of how astronomy could operate in an era of accessible technology and global connectivity. On November 8th, 2025, exactly 42 days after the initial intensification event, the 3I Atlas signal underwent a second dramatic transformation. Over just 36 hours, the radio emission strength increased by 300%, reaching levels that made the object detectable even by relatively modest amateur equipment. What had required sensitive professional telescopes to study now registered clearly on backyard arrays. The surge was so pronounced that some observers initially suspected equipment malfunction, before confirming that every telescope pointed at 3I Atlas was recording the same explosive increase. The timing corresponded precisely with 3I Atlas crossing the 1.0 astronomical unit threshold, matching Earth's exact average distance from the Sun. At this point, solar energy input reached maximum levels that the object would experience during its passage through the inner solar system. The correlation between signal strength and solar distance had become undeniable. Something about proximity to the Sun was driving the radio emission, whether through direct solar heating, interaction with solar wind and magnetic fields, or activation of systems that required solar power. The mathematical relationship followed a pattern that engineers would recognize immediately. Signal strength appeared to scale with available solar energy following an inverse square law, the same relationship that governs how sunlight intensity decreases with distance. At twice the distance from the Sun, available solar power drops to 1/4. The 3I Atlas signal had strengthened by factors that precisely matched increased solar energy availability as the object approached. This suggested the emission mechanism, whatever it was, operated with fixed efficiency in converting solar input to radio output. The surge revealed additional fine structure previously hidden below noise thresholds. Within each 7.3 second pulse, analysts now detected subtle frequency modulation, variations of just a few hertz that occurred in patterns repeating every 3 pulses. This modulation was too weak to have been detected at earlier signal strengths, but became apparent once the overall amplitude increased. Whether this represented new behavior or simply revealed details that had been present all along remained unclear. Polarization measurements also showed evolution. The alternating left-right circular polarization continued, but the transition between states became sharper, switching in less than 0.05 seconds compared to the earlier 0.1 second timing. The increased signal strength apparently allowed whatever mechanism controlled polarization to operate more decisively with better defined state changes. Most significantly, the second surge accelerated beyond simple correlation with solar distance. During the final 12 hours of intensification, signal strength increased faster than solar energy input would predict, suggesting some threshold had been crossed or some process had activated that added energy beyond direct solar contribution. The emission appeared to be feeding on itself, amplifying through positive feedback that was not captured in simple thermal models. Radio astronomers scrambled to adjust their observation strategies, realizing that 3I Atlas might undergo further unpredictable changes as it continued its approach toward perihelion. Equipment was reconfigured to handle stronger signals without saturation. Recording systems were upgraded to capture higher time and frequency resolution, now that signal-to-noise ratios permitted more detailed analysis. The object that had been mysterious when faint was becoming even more puzzling as it grew louder. The increased signal strength from the second surge enabled analysis that had been impossible earlier, revealing layers of complexity hidden within what initially appeared to be simple repetitive pulses. As signal-to-noise ratios improved, sophisticated processing techniques uncovered modulation patterns, variations in signal properties that occurred at multiple timescales, and suggested hierarchical structure far more elaborate than first observations indicated. The primary discovery involved amplitude modulation within individual pulses. Each 7.3 second emission was not a simple rectangular pulse turning on and off, but rather contained internal structure. Signal strength varied smoothly during the 6-second peak intensity period, rising and falling in patterns that repeated with remarkable consistency from pulse to pulse. Fourier analysis revealed that these variations occurred at frequencies of approximately 0.3 Hz, creating a gentle oscillation about 3 times per pulse duration. More intriguing was the phase modulation detected through careful frequency analysis. The carrier frequency of 1400.1 MHz showed microscopic variations, shifts of only a few hertz occurring on millisecond timescales. These frequency deviations were not random noise, but followed patterns that correlated with the amplitude modulation. When signal strength increased slightly, frequency shifted higher by proportional amounts. When amplitude decreased, frequency dropped correspondingly. This coupling between amplitude and frequency suggested the emission mechanism involved oscillating systems where multiple parameters changed together in coordinated fashion. The 7-pulse superstructure observed earlier gained new dimensions with improved data quality. Not only did peak amplitude vary across the 7-pulse sequence, but pulse width showed subtle changes as well. Pulse 1 in each sequence lasted approximately 7.28 seconds, while pulse 4 extended to 7.35 seconds. Differences of only 70 milliseconds, but consistent across hundreds of observed cycles. This pulse width modulation had been invisible at earlier signal strengths, but emerged clearly once the second surge provided better measurement precision. Polarization analysis revealed perhaps the most striking pattern. While the basic left-right alternation continued, the degree of polarization, the percentage of radio wave energy in the circularly polarized state versus unpolarized state, varied systematically. Even-numbered pulses showed 95% polarization, while odd-numbered pulses exhibited only 85%. This 10% difference might seem minor, but represented a significant and consistent asymmetry between alternating pulses that had no obvious explanation in natural emission mechanisms. Statistical analysis confirmed that all these modulation patterns were genuine signal characteristics, rather than instrumental effects or analysis artifacts. The patterns persisted across different telescopes, using different receiver technologies and different data processing pipelines. They showed temporal stability, remaining consistent over weeks of observation. They exhibited internal coherence, with various modulation types correlating with each other in mathematically describable ways. Information theorists examining these patterns calculated that the modulation structure could theoretically encode data at rates of several bits per pulse. Whether any actual information was present remained unproven, but the bandwidth and complexity existed to support data transmission if that was the signal's purpose. The patterns showed sufficient structure to be analyzed for information content, while remaining ambiguous enough that no clear message emerged from decoding attempts. The emergence of these patterns transformed the investigation. 3. I-Atlas was not broadcasting a simple beacon, but rather a complex signal with multiple layers of modulation, suggesting either remarkably sophisticated natural physics or deliberate engineering. Either conclusion carried profound implications. As evidence accumulated that 3 I-Atlas might represent more than natural phenomena, a contentious debate erupted within the scientific community about whether humanity should attempt active communication with the object. The controversy revealed deep divisions about protocols, ethics, and risks associated with responding to potential extraterrestrial contact. Divisions that had simmered theoretically for decades. but now demanded practical resolution. The pro-transmission faction argued that if 3I Atlas carried any form of intelligence or instrumentation capable of detecting signals, humanity had a responsibility to respond. The object would pass through the inner solar system only once, reaching perihelion in late November, before beginning its journey back to interstellar space. This represented a narrow window, perhaps humanity's only opportunity to establish two-way communication with whatever 3I Atlas represented. Remaining silent when confronted with possible contact would be a failure of nerve and curiosity that future generations might never forgive. Proponents suggested transmitting a simple mathematical sequence, prime numbers or geometric patterns that would be universally recognizable to any technological intelligence. The transmission could be directed at 3I Atlas using powerful radio telescopes like Arecibo's successors, broadcasting at the same 1400 MHz frequency the object was using. If the object responded by changing its signal patterns, that would provide conclusive evidence of artificial origin and establish the basis for more complex exchanges. The opposition raised multiple objections, both practical and philosophical. First, transmitting without international consensus violated established SETI protocols, developed precisely to prevent unilateral decisions about representing humanity to potential extraterrestrial intelligence. The decision to announce Earth's presence and technological capability to unknown entities should involve global consultation, not be made by individual research teams or nations acting alone. Security concerns loomed large in opposition arguments. If 3I Atlas was indeed artificial and represented a probe or vessel from another civilization, broadcasting powerful signals directly at it revealed Earth's location and technological level to entities whose intentions remained completely unknown. The history of contact between civilizations with technological disparities on Earth offered sobering lessons. Some argued that caution and observation were wiser strategies than immediate active engagement. Scientists also questioned whether transmission would accomplish anything useful. If 3I Atlas was natural, broadcasting at it would be pointless. If artificial, but operating autonomously without capacity to modify programming, it might not be able to respond. If capable of response, but following protocols that prohibited alteration based on local contact, it might remain silent regardless of what Earth transmitted. The chance of meaningful two-way communication seemed low enough that the risks outweighed potential benefits. The debate extended beyond scientific circles into public discourse. Media coverage brought the question to general audiences who had opinions about whether humanity should announce itself to possible cosmic neighbors. Online polls showed public opinion divided roughly evenly, with slight majority favoring transmission. Government space agencies received inquiries from legislators about what policies governed such decisions and whether existing frameworks were adequate. International astronomical organizations attempted to broker consensus through emergency meetings and working groups, but achieving agreement proved impossible. The various positions reflected fundamentally different risk assessments and values that could not be easily reconciled through discussion. As 3I Atlas approached perihelion, the question of whether someone would transmit despite controversy remained unresolved and increasingly urgent. By mid-November 2025, 3I Atlas had transcended astronomical journals and specialist publications to become a global media phenomenon. News coverage evolved from initial science section curiosities to front-page headlines and prime-time television features. The story contained all the elements that capture public imagination: cosmic mystery, potential alien contact, scientific controversy, and a ticking clock as the object approached its closest point to the Sun before beginning its exit from the solar system. Mainstream news organizations struggled to balance accuracy against the pressure for sensational headlines. Responsible outlets emphasized uncertainty, noting that natural explanations had not been definitively ruled out, and that scientific consensus had not formed around artificial origin hypotheses. Headlines carefully qualified claims with words like possible, mysterious, and unexplained. But even measured coverage could not escape the dramatic reality that an interstellar object was broadcasting organized radio signals that defied conventional explanation. Less scrupulous media outlets abandoned such restraint entirely. Tabloids declared definitive alien contact. Clickbait websites promised exclusive revelations about the object's purpose and origin. Social media filled with speculation, ranging from plausible to fantastical, with algorithms amplifying the most engaging content regardless of accuracy. Distinguishing legitimate scientific reporting from sensationalized fiction became increasingly difficult for general audiences. The visual media faced particular challenges. 3. Eye Atlas appeared in telescopic images as a faint smudge with barely visible tail, not the dramatic spacecraft or crystalline artifact that would satisfy visual storytelling needs. News producers resorted to artist renderings and computer animations that inevitably influenced public perception. Some depictions showed sleek technological constructs more appropriate to science fiction than serious journalism. These images became the public face of 3 Eye Atlas, despite having no basis in actual observations. Scientific communicators found themselves overwhelmed by media requests. Researchers who normally gave occasional interviews suddenly faced dozens of inquiries daily from outlets worldwide. The demand exceeded the community's capacity to respond while maintaining accuracy and appropriate caution. Some astronomers became regular media presences, their faces and voices becoming associated with the story. Others retreated from public engagement, uncomfortable with the spotlight and concerned about misrepresentation. The language barrier between technical astronomy and public communication created persistent misunderstandings. Concepts like statistical significance, confidence intervals, and provisional hypotheses did not translate well into news formats demanding clear binary answers. When scientists said an artificial origin could not be ruled out, headlines reported that scientists believe object may be alien probe. Subtle distinctions that mattered greatly to researchers got lost in translation to general audiences. International coverage revealed cultural differences in how the story was framed. Western media often emphasized scientific mystery and discovery. Some Asian outlets focused more on philosophical implications of cosmic contact. Coverage in regions with different relationships to science and technology showed varying levels of skepticism or acceptance of extraordinary claims. The media attention created feedback loops that complicated the scientific investigation itself. Researchers found themselves responding to questions driven by previous media coverage rather than by the data. Public expectations shaped by sensationalized reporting put pressure on scientists to provide definitive answers before analysis was complete. The boundary between scientific investigation and public spectacle blurred uncomfortably. Despite these challenges, the media firestorm served positive functions. It engaged millions of people with authentic scientific mystery unfolding in real time. It demonstrated that space exploration and astronomy remained capable of generating genuine wonder and excitement that transcended immediate practical applications. While public attention focused on scientific debates and media coverage, a quieter but equally significant response was occurring within government corridors. Multiple nations with space programs and defense establishments began treating 3I Atlas not merely as astronomical curiosity, but as potential national security concern requiring official assessment and classified analysis. The involvement of government agencies signaled that whatever 3I Atlas represented, it was being taken seriously at the highest institutional levels. The United States Space Force, established in 2019 and tasked with monitoring space domain awareness, began receiving regular briefings about 3I Atlas observations. While the organization's primary mission involved tracking satellites and orbital debris rather than interstellar objects, the radio emission characteristics triggered protocols designed to identify and assess anomalous space-based signals. Space Force analysts brought expertise in radio frequency analysis and signal intelligence that complemented civilian astronomical capabilities. NASA's Planetary Defense Coordination Office, normally focused on potentially hazardous asteroids, expanded its monitoring to include 3I Atlas despite the object posing zero collision risk. The office's involvement reflected recognition that planetary defense might encompass more than physical impact threats. An object demonstrating unexplained technological characteristics in near-Earth space warranted attention regardless of trajectory. Briefings reached the NASA Administrator's Office, and from there to National Security Council staff. International coordination occurred through channels separate from public scientific collaboration. Intelligence sharing agreements between allied nations included provisions for anomalous space phenomena. Five Eyes intelligence partners, the United States, United Kingdom, Canada, Australia, and New Zealand, established a working group specifically for 3I Atlas assessment. The group's deliberations remained classified, but its existence indicated that governments were preparing for various contingencies, including possibilities they were not yet ready to discuss publicly. Russia and China maintained their own parallel assessments. Chinese space authorities redirected observational assets to monitor 3I Atlas while maintaining public silence about their findings. Russian statements emphasized natural explanations while acknowledging the object's unusual characteristics. The geopolitical dynamics of potential extraterrestrial contact, a scenario long considered in theoretical frameworks, began playing out in practice as nations positioned themselves relative to information control and potential technological opportunities. The classification decisions themselves revealed government thinking. Initial 3I Atlas observations remained in open scientific literature, but certain analyses involving signal processing techniques and trajectory assessment became restricted. The boundary between public and classified information was not random, but reflected judgments about what capabilities governments wanted to protect and what possibilities they took seriously enough to restrict discussion. Military interest focused particularly on the radio emission characteristics and their implications for detection and communication technologies. If natural processes could produce such organized signals that had implications for distinguishing artificial from natural radio sources in space surveillance. If artificial, the technical specifications of the transmission system represented intelligence about capabilities of whoever built it. Either way, the phenomenon warranted careful study by organizations responsible for understanding potential aerospace threats or opportunities. The government involvement added another layer of complexity to the already complicated 3I Atlas situation. Scientific investigation continued in public view, but parallel classified assessment proceeded using resources and expertise unavailable to civilian researchers. What governments knew or suspected beyond public knowledge remained unclear, fueling speculation that added to the mystery rather than resolving it. The mere fact of substantial government attention suggested that official assessment judged 3 Ars-Ga Atlas significant beyond pure scientific interest. After months of observation, analysis, and debate, the astronomical community remained divided, but certain patterns in professional opinion had emerged. While no consensus existed, the distribution of viewpoints and the arguments supporting different interpretations revealed where the balance of evidence seemed to point, at least provisionally. Understanding the leading hypothesis required examining not just what was most likely, but why certainty remained elusive. The plurality position among researchers who had published analysis or spoken at conferences held that 3I Atlas represented an exotic natural object whose radio emission arose from physical processes not previously observed or fully understood. This view acknowledged all the anomalies while maintaining that nature produces phenomena stranger than current theory anticipates. The narrowband emission, precise timing, and modulation patterns might reflect complex electromagnetic processes in a highly unusual cometary body, with atypical internal structure and composition. This natural but exotic interpretation gained support from the multi-wavelength observations, showing that 3I Atlas behaved normally at every wavelength except radio. The optical, infrared, and ultraviolet signatures matched expectations for active comets. The outgassing rates and dust production followed predictable physics. Only the radio emission was anomalous, suggesting it was an addition to otherwise normal cometary behavior, rather than indication that the entire object was artificial. The solar distance correlation strongly supported natural processes. The signal intensification tracking available solar energy suggested the emission mechanism was powered by sunlight rather than by internal energy sources. Artificial probes operating for millions of years in interstellar space would presumably use nuclear or other long-lasting power systems, rather than depending on occasional stellar encounters. The solar-powered nature argued for natural phenomena triggered by thermal or electromagnetic effects of stellar radiation. However, a significant minority of researchers, perhaps 20 to 30% of those actively studying the object, concluded that artificial origin deserved serious consideration as the most parsimonious explanation. This view held that invoking unknown natural physics to explain every anomaly was less satisfying than acknowledging the signal characteristics matched those expected from engineered transmission systems. The frequency, stability, modulation structure, and polarization control all had obvious technological implementations, but required stretched interpretations to attribute to natural causes. The artificial hypothesis faced its own difficulties. No evidence of propulsion or navigation existed beyond the trajectory analysis that some found suggestive. no response to observation had occurred despite months of intense scrutiny. The object showed no signs of active maneuvering that would indicate controlled spacecraft rather than ballistic trajectory. If 3I Atlas was artificial, it was either dormant, autonomous with no capability for interaction, or operating under protocols that prevented obvious revelation of its nature. A third position, perhaps representing 15% of researchers, held that current evidence was genuinely insufficient to favor either natural or artificial explanations strongly. This agnostic view emphasized that unprecedented observations required extraordinary patience. Premature conclusions risked becoming entrenched positions that would bias future interpretation. Better to acknowledge uncertainty and continue observation than to declare confidence where none was justified. The leading hypothesis, if one could be identified, was that 3I Atlas represented natural phenomena on the exotic end of the spectrum, but with confidence levels too low to close the question. The object remained genuinely mysterious, resistant to definitive explanation, and likely to remain controversial until either additional evidence tipped the scales or it receded beyond observation range with questions unresolved. Even if 3I Atlas ultimately proves to be entirely natural, the implications for physics and astronomy would be revolutionary. The discovery of natural processes capable of generating such organized radio emission from cometary bodies would require substantial revision to understanding of electromagnetic phenomena in space, and would open entirely new research directions into exotic physics operating under conditions rarely encountered. The existence of stable narrowband radio emission from a comet would demand explanation through mechanisms not currently part of standard astrophysical theory. Textbooks would need new chapters describing how specific combinations of composition, structure, magnetic fields, and thermal cycling can produce coherent electromagnetic oscillations. The physics would need to be worked out from first principles, requiring laboratory experiments to reproduce the conditions and test proposed mechanisms. Universities would establish research programs dedicated to understanding this new class of natural radio sources. Cometary science would undergo fundamental reassessment. If one interstellar object exhibited these properties, others presumably could as well. This would mean that past surveys had missed an entire category of electromagnetic activity because observers were not looking for it or lacked the sensitivity to detect it. Future comet observations would routinely include radio monitoring, searching for similar emissions from solar system comets, or additional interstellar visitors. The discovery would expand the known phenomena associated with these primitive icy bodies. The mass estimates and density calculations, if confirmed, would revolutionize understanding of interstellar object populations. 3I Atlas would demonstrate that massive objects could be ejected from planetary systems and survive for potentially millions of years in interstellar space. This would require recalculating formation and ejection rates for such objects, and might provide evidence for planetary system architectures quite different from our own solar system. The object would become a probe of alien planetary formation processes, carrying information about conditions in distant stellar environments. The chemical composition, particularly the high carbon dioxide ratios and exotic volatile signatures, would provide unique data about material formed in the outer reaches of other solar systems. Laboratory astrochemistry would gain new constraints on molecular formation pathways in extremely cold environments. The chemistry might reveal clues about the age and metallicity of the parent stellar system, offering indirect evidence about stellar populations in regions of the galaxy that are otherwise difficult to study. Detection technology would advance rapidly. If natural objects can produce signals mimicking artificial transmission characteristics, search for extraterrestrial intelligence programs would need to develop more sophisticated discrimination methods. New criteria would be established for distinguishing genuine techno-signatures from natural electromagnetic organization. This would actually strengthen SETI methodology by forcing more rigorous standards for claiming detection. Perhaps most profoundly, discovery that nature can generate such apparent complexity and organization without intelligence would provide humbling reminder about human tendency to see design where none exists. It would demonstrate that the universe contains physical processes capable of producing order and pattern through purely natural mechanisms more sophisticated than current theory anticipates. This would be simultaneously disappointing for those hoping for extraterrestrial contact and exhilarating for those who find nature's capabilities endlessly fascinating. The natural explanation, far from being the mundane or boring outcome, would expand the known possibilities of physics and reveal that the universe still holds fundamental surprises about how matter and energy behave under exotic conditions. If 3I Atlas is confirmed to be artificial, the implications would extend far beyond astronomy into every domain of human thought and activity. Such confirmation would represent the most significant discovery in human history, fundamentally altering humanity's understanding of its place in the universe and forcing reconsideration of assumptions that have shaped civilizations for millennia. The immediate scientific impact would be transformative. Confirmed detection of extraterrestrial technology would prove that life and intelligence are not unique to Earth, that the process producing technological civilization has occurred at least twice in cosmic history. This would shift the Drake equation parameters from speculation to data-driven analysis. If intelligence emerged independently in at least 2 locations, the universe likely contains millions or billions of technological civilizations at various stages of development. The technology itself would become subject of intense study regardless of whether direct interaction occurred. The engineering required to construct an object capable of crossing interstellar space, surviving for potentially millions of years, and operating autonomously represents capabilities beyond current human achievement. Analysis of the radio transmission system, power generation method, materials science, and navigation technology would provide glimpses into what advanced engineering looks like. Even without direct communication or physical access, remote observation could yield insights that accelerate human technological development. The existence proof would revitalize space exploration and SETI programs. Governments would dramatically increase funding for programs searching for additional evidence of extraterrestrial intelligence, knowing that the search was no longer speculative, but rather archaeology of a populated cosmos. Public support for space science would surge as humanity collectively recognized the importance of understanding the neighborhood it inhabits. The search for life on Mars or the moons of Jupiter would gain urgency as pieces of a larger puzzle about how common life might be. Philosophical and religious frameworks would face significant challenges and opportunities. Major religions would need to integrate the reality of other intelligent beings into theological structures built on assumptions of human uniqueness or special creation. Some traditions might adapt easily, while others would experience profound theological crisis. Secular philosophies would grapple with questions about the nature and diversity of intelligence, ethics of contact with non-human minds, and humanity's responsibilities in a populated universe. The geopolitical consequences could be profound. Confirmation of artificial origin might unify humanity around shared identity as one civilization among presumably many, potentially reducing emphasis on national and cultural divisions. Alternatively, it could exacerbate competition as nations and factions positioned themselves to gain advantage from any technological insights or future contact opportunities. International cooperation frameworks would face tests for which no precedent exists. Cultural production would explode with artistic, literary, and philosophical responses to confirmed contact. The creative exploration of what this means for human identity, purpose, and future would generate works spanning all media and genres. Education systems would need to incorporate cosmic perspective into curricula, teaching children that humanity inhabits a universe where intelligence and technology are not singular achievements. Perhaps, most importantly, confirmation would force humanity to confront the Great Silence, the Fermi paradox made more acute by actual contact. If technological civilizations exist and build interstellar probes, why is the galaxy not obviously teeming with evidence of their presence? 3I Atlas might represent first detection in an increasingly obvious phenomenon. Or it might be an extraordinary rarity that raises more questions than it answers about cosmic habitability and civilization longevity. As November 2025 progressed toward 3I Atlas's perihelion passage, astronomers worldwide recognized that the window for detailed observation was rapidly closing. After reaching closest approach to the Sun on November 24th, the object would begin its journey outward, gradually receding in both distance and brightness until it faded beyond detection capability of even the largest telescopes. This created an observational race against time, a scramble to extract every possible measurement before the opportunity vanished forever. Telescope time became the most precious commodity in astronomy. Major observatories received emergency proposals requesting immediate access to study 3I Atlas while conditions remained favorable. Review committees faced unprecedented pressure to allocate time to this unique target while balancing commitments to other approved programs. Some facilities implemented special scheduling to allow 3I Atlas observations during brief gaps between other projects, maximizing data collection without completely disrupting normal operations. The James Webb Space Telescope, humanity's most powerful infrared observatory, devoted substantial time to 3I Atlas during the critical perihelion period. The observations aimed to capture thermal evolution as solar heating reached maximum intensity, searching for any changes in surface temperature distribution or outgassing patterns that might correlate with radio emission behavior. Every hour of Webb time was planned to maximize scientific return, with backup plans prepared in case the object showed unexpected activity requiring rapid response. Radio telescope networks maintained continuous coverage as the signal strength peaked. The Very Large Array in New Mexico, ALMA in Chile, and facilities across Europe, Asia, and Australia coordinated observations to ensure 3I Atlas remained monitored 24 hours per day. The data stream flowing from these observatories reached unprecedented volumes, requiring dedicated computing clusters to process and analyze the information in near real time. Optical astronomers pushed equipment to its limits, attempting to resolve surface features on the nucleus. Even at closest approach, 3I Atlas subtended only a fraction of an arcsecond, requiring the best atmospheric conditions and sophisticated adaptive optics systems to achieve useful spatial resolution. The goal was to detect any asymmetries or distinct surface regions that might correspond to radio emission source locations, providing crucial clues about the physical mechanism. Spectroscopic observations intensified to characterize chemical composition with maximum precision. Every molecular species detectable in the coma received detailed analysis. Isotopic ratios, particularly ratios of deuterium to hydrogen or carbon-13 to carbon-12, could provide information about formation temperature and stellar environment where 3I Atlas originated. These measurements required high spectral resolution and long exposure times, both demanding resources in short supply. Amateur astronomers contributed to the effort by maintaining photometric monitoring, tracking brightness variations with timing precision that supplemented professional observations. The distributed network of backyard telescopes provided temporal coverage that no single professional facility could match, creating a continuous record of optical activity throughout the perihelion period. Mission proposals for future spacecraft encounters with interstellar objects received urgent attention. While no probe could be launched in time to reach 3I Atlas, detailed study of this object informed mission design for future opportunities. What instruments would be needed? What measurements were most critical? How could spacecraft be designed for rapid deployment when the next interstellar visitor appeared? The race reflected astronomy's fundamental dependence on transient opportunities. Unlike laboratory experiments that can be repeated at will, astronomical phenomena occur on their own schedules. 3I Atlas would pass through once and never return, making every observation precious and every missed opportunity permanent. As of mid-December 2025, 3I Atlas continues its journey outward from the Sun, having passed perihelion on November 24th, and now receding into the outer solar system along the hyperbolic trajectory that will eventually carry it back to interstellar space. The radio pulse that captivated the world still broadcasts with the same 11.7-hour periodicity, though gradually weakening as solar distance increases and available energy diminishes. The object that arrived as a silent giant has become a talking enigma, and its voice has not yet fallen quiet. The signal strength peaked at perihelion as predicted, reaching levels that made 3I Atlas briefly one of the brightest radio sources in Earth's sky outside the Sun and Jupiter. Since then, the emission has declined following the same mathematical relationship with solar distance that characterized its rise. By early December, signal strength had dropped to approximately 40% of peak intensity. Current projections suggest the transmission will remain detectable by major radio telescopes until late January 2026, when 3I Atlas crosses beyond 2 astronomical units and the signal fades into background noise. Analysis of data collected during perihelion passage continues, with new papers appearing weekly as research teams complete processing of their observations. The scientific literature is slowly filling with detailed characterizations of signal properties, refined mass estimates, spectroscopic measurements, and theoretical modelling attempts. Peer review proceeds with unusual speed given the high priority and intense interest, but definitive conclusions remain elusive. The mystery has been thoroughly documented, but not solved. No consensus has emerged about natural versus artificial origin. The distribution of professional opinion remains roughly where it stood in November. Plurality favouring exotic natural processes, substantial minority arguing for artificial explanation, and significant fraction maintaining genuine uncertainty. Additional data has not resolved the ambiguity, but rather has provided more detailed description of the phenomenon that requires explanation. Both camps can point to aspects of the observations that support their interpretations. Several governments have indicated plans for dedicated missions to study future interstellar objects, with 3I Atlas having demonstrated both the scientific value and practical feasibility of such encounters. Spacecraft designs are being refined that could launch within months of detecting incoming objects, reaching them for close-up study before they exit the inner solar system. Whether such missions would definitively resolve questions like those posed by 3I Atlas remains uncertain, but the commitment to trying represents significant shift in space exploration priorities. The broader impact on human culture continues to unfold. 3I Atlas has become a reference point in discussions about humanity's cosmic context, a tangible example of how quickly assumptions about solitude or uniqueness might be challenged. The object has inspired art, literature, philosophical discourse, and vigorous public debate about how humanity should respond to genuine ambiguity about potential contact. Perhaps most importantly, 3I Atlas has demonstrated that the universe remains capable of surprising us. In an era when some claimed that astronomy had entered a phase of incremental refinement rather than revolutionary discovery, an interstellar visitor arrived broadcasting signals that defied immediate explanation. The cosmos proved once again that it contains phenomena stranger than theories anticipate. As 3I Atlas fades from Earth's telescopes and resumes its journey through the dark between stars, it leaves behind more questions than answers, but also renewed appreciation for the profound mysteries that still await discovery. Somewhere in the radio spectrum, the pulse continues, growing fainter with each passing day, but carrying its secrets back into the cosmic night from which it came. Whether those secrets involve exotic physics or extraterrestrial engineering, whether they will ever be fully understood or remain forever ambiguous, the object that began as a silent giant has earned its place in the history of human exploration and wonder. The pulse continues, the questions remain, and humanity watches, listens, and waits for what the universe might reveal next.